Hi there everyone. So today I'm going to be covering this paper by Timothy P. Lilligrap, and it was actually published in Nature. And this is like a pretty cool paper, and it's like something which you don't expect to really work, but turns out that this idea really works, and that's why like I'm really interested in this. So now one thing like which I did notice really good about this paper is that Timothy P. Lilligrap wrote this when he was at the Department of Pharmacology, University of Oxford, and also he was at DeepMind. So I guess this is like the time when he was actually making his academic stint along with his debut in Google DeepMind. And now Google DeepMind is like a very funny sort of company because they do work on like a lot of fun foundational problems, and it is like really tough to like find such people. But yeah, that's all I can do, right? Like just read their papers and try to learn from that. But anyways, like, so the key point is that this is like a paper which actually fixes the weight transport problem, which is a method to fix the weight transport problem which we discussed earlier. So let's get down to it. And obviously, like, I am not gonna read it word by word, but by the end of this video, I do hope that I will be able to deliver the core insight. So the the title of this paper is Random Synaptic Feedback Weight Support Error Backpropagation for Deep Learning. And it's like the title really seems like a mouthful, but like the idea is like very it's motivated like by biology. So let's first look at like what the problem is. Okay, and so consider like this A figure, and it's like a standard figure. What it means is, so let's say that you have three layers. One is like layer 1, one is layer 2, and one is layer 3. So now consider like how does like standard backpropagation update the weights in this layer. So what you generally have is that, let's say for this layer you have like a error signal E, right? This is like the error signal which backpropagation has computed in a higher layer, and you want to like update the synapse at this particular point. So the point is like how do you like propagate the error signal from higher layer to the lower layer, and then how do you like update actually this synapse, right? And that's like the whole idea of backpropagation. So it turns out like in case of backpropagation, what happens is that, so let's say this error signal E is actually like the gradients at this higher layer, and you need a way to like propagate these gradients to the lower layer. And if you like apply a standard chain rule, then it turns out that there is like this weight transpose operation which the normal backpropagation algorithm does. And let me try to explain that in my notes so that it becomes clear. Okay, so basically what happens is that in case of like, for example, uh, okay, so let's say that you have a neural network in which like you have a network with input X, and then another layer which is having a weight matrix W naught. And then let's say that you have like another layer which is like a weight matrix of W, and this W neuron is actually like the output layer. So this is like the output layer, this is like the input layer, and this is like this is one of the very simple form of neuron in which like there is just one hidden layer. So this is like a standard neural network, and we are gonna see like how standard backpropagation algorithm works. So what happens is that in normal case, like you compute like this error E at the output, and your error is nothing but just like it's just like a L1 norm, like how far you are from a target Y star. And then if you want to like minimize the error, like generally what you end up doing is like you end up squaring this error. And like in case your output variable Y has, let's say, 100 dimensions, then you can imagine that you have like a vector of 100 dimensions, and then you take like a transpose of that, and then you multiply both of these. So it essentially means like you are taking like some sort of squared of each elements and then summing that up, and that is like what standard dot product is. And if you do that, that actually helps you like compute like the loss which you have. So in this case, like your network is like standard neural network with one hidden layer, on which like you're trying to do L2 error, right? So now the point is that let's focus on like how does like normal backpropagation work. So in normal backpropagation, if you have to let's say update this layer, let's say if you have to update this layer, then the amount of weight update which you need to make to like every to the weights of this layer is actually directly proportional to this error signal multiplied by the incoming activity, which is H transpose. And this is something which I already discussed before. So you imagine, so in this case, like in backpropagation, if you have to update the weights of any layer, you have the gradient signal coming from the higher layer, and then you multiply that with the input activity which comes in. Uh, so let's say this is like a neuron F. So generally, like if you are to make this del L by del W at this way, here it will be directly proportional to EH transpose times F dash H. And the problem is in this case, like we are assuming that y is equal to x. So like this is a neural network with linear neurons. So y equal to x is the activation. So F dash H is 1. So that's why you can remove this part of the equation, and that directly gives you the error which is incurred in this particular region, which is minus E H transpose. Now let's imagine, so that's like how you train the weights of the output layer, and obviously you don't need to train the weights of the input layer because that's essentially like the input, right? It has no weights, but there is one hidden layer which you need to update. And how will the weight update at that layer look like? So in this case, what happens is that you can apply a standard chain rule. So gradient of loss with respect to the weights of the hidden layer is nothing but gradient of loss with respect to the hidden activity and gradient of hidden activity with respect to the weights, right? So now if you see here, the first term, the gradient of loss with respect to hidden activity, is essentially it's essentially like the error signal E multiplied by the transpose of the weights. And this is what is actually happening here. So in this case, like if you have to update the weights at this layer, the final expression like of weight update will be pretty complex, but like it can be easily understood. So in this case, what happens is like you have a error signal E, and then you're gonna, so you have like this error signal, so you have like this 3-layer neural network, and in this case the output, you have an error signal E, and if you multiply it by the weights, if you multiply it by the weights of this layer, so if you multiply the error signal by the transpose of the weights of the higher layer, then you get the error signal del at this particular point. And the key point is that you need to like take this transpose of the weights, and in backpropagation, like in biology, there is no way to take the transpose of these weights. So if you have to, so one key takeaway from this discussion is that if you have to take like, if you have to consider how like a standard neural network is optimized, you have like a error signal which you multiply by the transpose of the higher network layer along with incoming activity X at that particular point. So in this case, like X is this particular activity which is sent as the input to the network. So the idea of, so now the key point is that in a standard neural network, let's say in a standard neural network, let's talk about like how like this error signal is generally delivered. So what happens is that in this case, like let's say you have like a neuron like this, and it's connected to like 3 other neurons in a higher layer. So let's say that you have a error signal here, right? Now the key point is that for this error signal to actually propagate back, you need to like multiply this error signal by the transpose of the weights, right? And this gets non-biologically plausible because in that case, like the network needs to compute like this W transpose in memory. So another idea is that let us build like another kind of network in which like there is a separate network which is responsible for delivering this error information. So in this case, what we have is like we build like another kind of neural network, which I will say in case of like yellow. So this, what this yellow kind of neural network, let me make it in pink so that it is more legible. So what this kind of neural network does is that it receives like the error signal from the higher layer, and then it is, so like let's say the forward weights are W, So then in this case, this network contains like the weights W transpose, and it's like a separate network, and its weights are like transpose of the forward weights, and that actually gives you like the error signal of this particular neuron. And you can directly deliver like this error, you can directly deliver this delta to the neuron whose synapse you are trying to update. So in this case, you are trying to update this synapse, so you need to know how much. So let's say this synapse has, let's say, four incoming connections. So then your error signal will tell you how much the weight on each of these connections will change, right? And that's the sort of computation you do. So you have like this separate kind of error delivery network which can deliver like the correct errors to the neural network. But here is where like the problem gets really interesting, and let's jump back to the paper to see what they are saying. So here, like in standard backpropagation, you have two kinds of networks. One is a feed forward path and one is a feedback path. And then in the feedback path, like you have a network which essentially computes like the transpose of these weights. And the problem is that in the brain, there is no evidence that you compute this transpose. So the core idea of the people in this paper is that what they assume is that you can assume that there is another kind of like separate feedback network. This is called a feedback network, which essentially has like this kind of weight. It has a random weight b, and this network is actually responsible for delivering the error signal. So what they're saying is that in case like your feedback network does not even, it does not contain like the transpose of the forward weight matrix, then even then, if it's just random, like the learning can still happen, and that's like a really good thing. So so let's like try to understand like how it works. And so the idea is like pretty simple. Let me go back to my notes. Okay, so now we are back at their paper, and let me try to explain like intuitively what is happening here. So let's say that you have like two ways in which you can deliver the error. So one is like a standard backpropagation way, and one is the way which these authors are talking about. So let's say that you have in, so let me draw in this in black. So let's say like you have a neural network, and you are trying, so this is like the error signal at the output, and this is the layer which you are trying to update. So in this case, like the error signal like which you will try to deliver here, and let's say this is like W and this is like W dash, these are, so this is the layer you are trying to update, and you want to deliver the error to this particular neuron. Okay, so in this case, the error signal which a standard backpropagation net will carry in like the separate error delivery network will be like W transpose W transpose E. And but the problem is like this sort of different feedback connection does not contain like, it does not carry like transpose. So like there is no way like the brain does transpose of the matrices. So what we do is like we can what these authors are saying is that we can have like a, so let's say we will just copy our neural network, and what they say is that they can define another kind of feedback network, and this feedback network is like maybe drawn in yellow. Let me make it in magenta. So this error delivery network is drawn in, let's say, magenta, and it contains like weights B, and these weights are random. These weights are not equal to W transpose, like they are just random weights. And this, so the error which is like delivered by these by this sort of randomly initialized network will be BE. And now the point is that if this BE turns out to like approximate like W transpose E really well, then we are learning like a really good learning algorithm. So we are actually learning how to deliver these error signals in a really correct way. So so you can imagine that this B times E is like a vector 1, and this W transpose E is like another vector 2. And if you take like a dot product between, so if these two vectors are going to be like essentially equal, then so then these vectors will be like having almost like zero angle between them, and if they are like very different, they will have like a 90-degree angle between them. So what the authors are showing here is that if you like train like a, if you, let's say you have a neural network which has these three layers, and you are delivering like the error through this kind of neural network which is like initialized with random weights, and you are looking at this signal BE, and you're looking at another signal W transpose E. So because like during forward pass you know what's W, so you can compute transpose, and then there is one BE signal which you have. So what they're saying is that so let's say you train your network for 10 iterations, and at every iteration you are computing W transpose E, and you're also computing BE, and then you're taking like a dot product between them. And if it turns out like that this dot product is like 0 or very close to 0, it means that the error which you are approximating by this separate error delivery network is similar to what like you would have done if you had like a error delivery network which essentially contained like the transpose of this weight. And the point is like so this is like the whole idea that you substitute the backward network, the backward feedback network, with weights which are just transpose of it, and you don't even need to train this network. Like this is just like some random network with some random weights beta, and this can be used to deliver the error signal. And even if it is never trained, the forward facing network W dash and W end up like ending up learning representations that do well on the given test data. So let me give you quickly like this. So let me quickly show you this figure. So like let's say you, so here it's the same thing that they have an input neuron XI activity coming in, they have a layer, and this is like the hidden output from this neuron, and they have like a error delivery network which is separate connections from the forward facing network. And that's because in brain like sometimes like the neurons definitely don't use like the same path to carry the information, and there are like separate bottom up and top down connections. So this is like top down connection, and this is like bottom up connection. Now the key point is that this B is like randomly initialized, and it is used to like deliver the error, and this network is always kept like frozen. So it's the lock here, and this network's weights B are not trained at all. And we look at that dot product which I discussed earlier, and it turns out like it's pretty cool. So what they're saying here is that they have like a linear problem. So they have like a neural network which contains like only like y equal to x activations, and they're trying to perform like a linear regression task. And what they do is that they show that if you use like error delivery through normal backpropagation, and then error delivery through this sort of like feedback alignment in which like the reverse top down network has just random weights, they say that the feedback algorithm actually performs better than backpropagation, which is really well. And this is like really interesting. And similarly like this is like a plot, like as you increase the number of examples, like what's the dot product between that signal which is W transpose E and then B times E, like what's the dot product between these two vectors. And as you can see like this dot product goes down to like almost like uh, 30 degrees or something, but it does not become perfect zero, which is fine because like you are still learning something which is very close to backpropagation, but we are not like we are not computing like a perfect inverse. So that's the point. So in this case like if B was the exact transpose, then these two matrices would have been same and the dot product would have been 0. But like if you just deliver the error with some random weight, then the dot product is low, like 30 degrees, but that's fine. And they are saying that the learning still works. So that's the key point. And what they are saying is that this actually proves biologically that so if the angle is non-zero, feedback alignment can still obtain similar levels of performance to backpropagation. And so this is very good for our understanding. So earlier, like we used to understand that if you have a neuron and it's connected by, so if this network is connected by 3 neurons, then during backpropagation, you have to use like the same connection to pass in the error information. And during like, while you're pumping the error information, you have to take like the W transpose and multiply the error signal at higher layer to get the error signal for lower layer. And that seemed to be like an argument which was against biology. But in this case, what they're saying is that if you don't reuse this connection, and if you just have a network in, so if this is like the forward network, you still have like a backward network, which is like having random weights b, the network will still manage to converge. So this is like this is like a justification of how, like, in the brain there are bottom up and top down connections, and it stands to reason like these top down connections are actually propagating this higher level information, like higher level error information. And their algorithm says that in a extreme case, like even if like you never train this, even if you never train this random matrix, thus learning still happens. And that's like really good. And since learning still happens, then that means that during the like the network which carries the error signal does not need to have w transpose signal, and it still works. And that's a biological justification of why like you can still deliver error without like taking the transpose of the forward weight matrix in this case. Now there is like one key problem here, and uh, let's uh, so let's talk about that a little bit. So the key point is that so so the key point is, like, if like the backward network is never trained at all, if the backward network is never trained at all, then how come like the learning can still happen? And that's like a curious question, right? So if you have like a neural network, a forward network, and then a backward network, and you compute like the loss, and backward error delivers this error, then, and backward network is never trained, then how can this sort of algorithm still work in practice? So it turns out that there are, so you can split like the learning into two phases, in three phases according to the paper. And what the learning actually looks like is that so it's divided into like these three phases. So the phase is as follows. So initially, like, you freeze this, so you have a three-layer neural network. So this is like the input layer, this is the output layer, and this is the hidden layer which you're trying to update. Now what happens is that you first, like in the first phase, you freeze like this weight w, and then your error signal is like whatever like activity your neural network was having, and then you feed like the error signal through this network, right, this b times e, and then you update like w naught, right? And then what happens is, like, as soon as this w naught, so this w naught already contains like the information of error b times e, which was delivered from this higher layer. And so now the new activation which you compute like after the forward pass, that will actually control like how, like, what is the output of this neuron, right? And that will impact like the output of this particular neuron. And when you update this weight matrix w after that, it already contains like the error information. So this is like a piping mechanism, in which, like, what happens is that initially, like, when you made forward pass, w not contained no information, then w didn't contain any information. But then once you computed the error, then at that time, like, when you delivered this error here, w not updated, and after that w updated, because like w not was updated in a correct way. So that is what, like, they are saying, and that's what, like, they are trying to show here. So as you can see, like, here the network is alternating between, like, initially w is frozen, w not learns, and then w learns, and w not is frozen, w is frozen, and w not still learns. And that's like a really good thing, and that's how they are able to do this. So here, like, what they're saying is they are able to train like a network on MNIST, and using this type of feedback alignment algorithm, and it really works well. So this is what, like, so this is like the key takeaway from their paper, that B only needs to act like W transpose, and feedback alignment demonstrates that this requirement is almost trivial to meet. So so the point is that in this case, like, if you just have a network and you define like a error network, which is just the transpose of the which is like just the which is like having just random weights, you can still manage to converge upon like a very good representation, and that is like really good. Okay, and that's the key point. Okay. So the point is that if you just build a neural network with this type of top-down delivery mechanism, which consists of random weights, then you can have this type of like feedback alignment where like the type of error signal which your feedback network delivers, which is like beta times e, is approximately equal to W transpose E, and which is like a actual error signal which would have been delivered by backpropagation, and this emerges even if you do not train B at all. And the fact that you don't need to train this reverse network B at all is actually really surprising, and it's like I would say it's one of the key breakthroughs in this direction. So one key takeaway is that if you build a network in which you give it like the forward machinery, and then a separate machinery, a separate module which contains like top-down connections, and you deliver like the error information through that, then your network will learn signals which are like approximately what you would have learned through chain rule. And that is like really that's like really nice thing to have. So in this way, like you can deliver errors and you don't need to use chain rule at all. So you don't need to compute like these separate gradients anymore. You can just deliver the errors information through these top down connections. Okay, so now that we are clear on this, I would also like to talk about uh, like what's like one limitation of their approach. And the limitation is like the pathways operate synchronously. And what does that mean? So let's talk about that in a little detail. So let's say that your neural network has these four neurons which are in parallel. Okay, so what they're assuming is that if you do like a forward pass, that each of these neurons has like a separate weight, and then the error delivery network is essentially sending like a error signal to each of these neurons, right? So you have like a error delivery network which takes like a signal from all these neurons, and then it sends that signal to all the neural networks. So in this case, you have like you have these four separate neurons which are mirroring the architecture of the front facing neurons, and then you are actually delivering like the precise error information to each of the neurons. So in this case, if you have four neurons in the forward pass, you are delivering like the error information in all four of these neurons, which means that your top down and bottom up network structures should be essentially equal to each other, and like the top down connection should mirror whatever structure of like bottom up neural network is. So the point is that if this was really true in the brain, then what we would have discovered is that we would have seen that okay, there is this one structure, there is like this structure one, like the way the synapses are connected, and then there is structure 2 which is also similar to the way the synapses are connected, and these are like two identical structures. So we will essentially have like these two kind of webs in our brain where one structure is equal to another. One is actually carrying the feed forward activities, and another is actually carrying like these backward activities, the error signal. So but that's not true, like we don't see that in our brain. Like we don't see these kind of equal equal things happening in the brain. So generally, like what in the brain we see is that we have like a lot of these neurons. So we have like a lot of forward facing neurons, and they form like this collection of neurons. And then there are only some connections which are top down, which are actually delivering this kind of information. So the top down connection is only delivering information to a community of neurons, and like it does not have any identical structure to what like these front forward facing neurons have. And but it's still somehow managing to deliver the error it's somehow managing to deliver some information which is helping these neurons learn. And that is like the key point, that the algorithm we discussed does not work if we have like some neurons to whom the error signal is not delivered at all. So then how do you update those particular set of neurons? And that actually remains like a key question which these people have like not discussed about. And there is like one other problem which is known as the neuromodulation problem. And let me explain that. So let me explain that from my end, and that will make it like a little bit clearer. Okay, sorry. Okay, so let's say that you have a neural network in which, like, so what was I talking about? Let me just try to remember it. Okay, so this idea is known as like the memory storage mechanism. And in memory storage, like what generally happens is there is like a standard assumption on which we base the design of neural networks. And the assumption goes as follows, that every connection has a weight W. So you change the W, you change the weight, and that will in turn change like the activity which your neuron is outputting, which is the activity Y. And in turn, it will incur some error, and then you will change back this weight again, right? And then as you are like learning, so as you are learning on a particular error, what happens is like you are making these weight changes, and gradually you are getting close to the correct answer. So the point is that the error mechanisms we have right now, so whenever you are feeding the error information back in, you're making changes to the weights, which in turn changes the activities, which in turn changes like the output. But like sometimes what happens is that, so this weight, so you can imagine that there is like this structure, right? And in this, like this is a weight space. So initially you are here, and if you have to get to the bottom of the loss energy landscape, you have to make like a lot of steps. But the problem is that sometimes like there are situations in which like you need to make like some very fast decisions. So what I mean by fast decisions is, let's say you saw an object coming and you just want to hit, you just want to stop rapidly. And if you want to change like these weights, if you want to make like these very fast decisions, then you need a mechanism to actually change these weights very fast. But the point is that you can't change these weights really fast, because let's say you have learned like some representations. So let's say you have learned some representations on a billion samples, and like at a particular moment, then you need to make like a rapid decision. And then these weights are actually, if you fluctuate these weights a lot, then what it will do is that it will forget whatever it has learned before. So you can't really make a lot of changes in the weight space, but rather like there should be a mechanism in which what happens is that this activity Y is actually changing on its own. So basically the idea is that when you are making like a forward pass, you have like a standard weight changes, like, so this has a weight and this is the activity Y. And then when you are computing a error, then this error should actually define two things. It should be able to tell you that, okay, this is the error, how much change should be made to the weight. And then there should be like another mechanism which says that, oh, so this is like a really emergency situation, and how much change needs to be made to the neural activation. So the key point is that when a neural network is learning based on the data, it sees like some sort of surprising situation. And then if it sees something surprising, obviously it can't add that surprising thing to the weights, because it will like shock the weight space and it will forget like whatever it has learned. So rather than accommodating that kind of like fast memory inside the weights, we need like a kind of fast memory which can actually change these activations really rapidly. And obviously like once it does that, then finally we can change the weights to respond with a slightly higher gradient in the direction of the surprise notion we have. So this is like a very intuitive idea. So let me summarize this again. So the idea is that if you have like, so let's say you have a weight and you have a connection, and you are trying to deliver an error, and you are like somewhat far away from like some, so your error is very large. Now the way you can improve the error is like you can directly increase Y by a very large amount, or you can make like just some small change to the weight. So the point is that it is easier for the neural network to make rapid decisions by fluctuating its activity y from y plus delta, rather than directly changing the weight. So if you want your neural network to make like these rapid decisions, then you cannot make these weight changes, and you need a mechanism to make these fast changes in the memory only. And that is something which is known as slow fast memory. And I will discuss that idea uh, later in a later video, and it seems like a lot of fundamental work will come from that direction. So let me navigate in this paper and show you where the authors did did talk about like about this thing. So let's talk about this. Okay, so they say that in so it is interesting that experimental evidence has shown that various third factors can modulate the magnitude and sign of synaptic plastic mechanisms. So what they're saying is that there are some things which are able to change the activities of a neural network, the hidden activities, other than just changes to the weights, and that is like what I am talking about. So if you can build like that sort of mechanism, it would be really cool. So not all the changes in activities have to come from weight changes. It has to be like something which happens really rapidly to the current neural activities which you have in the neural network. Okay, so this is really good. And okay, so this is fine. And let's move on to the next page. Okay, so the key point here with which like the authors end the paper is that so let's talk about like this nature of top down and bottom up connection. So we have these bottom up connections in the brain which carry like these activities, and then we have like a top down connection. And in this case, like the top down connection is only delivering the error information. So it's only delivering like it's only transforming the error signal E to like to B times E, and it's only transforming that by like a certain amount. So there is like one neural network which is carrying like the activity information, and then there is one neural network which is carrying the pure gradient information. So there so you can see like the bottom up is specializing in feed forward activities, and the top down is specializing in piping like the gradients or like the error information. So it is not clear in the brain how does whether this top down is actually responsible for purely delivering error information only, or is does it deliver like something else which we are not like which we are not familiar with that much. Okay, so that's another point. So what they are saying is that, for example, in our simplified models, the error signals modulate the synaptic strengths of feed-forward connections without affecting the post-synaptic activities. So that's what they are saying, that in their case, like they are just modifying the weights of the neuron, but they are not modifying the activities rapidly. And that is the kind of like fast memory storage which I was talking about. And turns out this idea has been used a lot in meta learning, and it was also originally termed as fast weight programmers by Jürgen Schmidhuber back in the 90s, and I will come that to in a later point. Okay, so now that this is like done, so this was like the whole paper, and the one line takeaway from this paper is that the brain contains bottom up and top down connections, and the top down connections actually help us deliver the error information even if we don't train a top down network. By we just initialize it randomly, we can still deliver error information to a neuron. And what happens is that the weight matrix of this top down neural network ends up to look like very similar to like the transpose of the forward matrix, and you don't really have to compute this this transpose operation on like in computer, and that makes it like more biological plausible. And the key point is that in this case we have separated the neural network into two parts: bottom up pipes activities, and the top down pipes the error signal. And it remains to be seen like how to design this top down neural network so that like it can either rapidly change like the activations themselves, or it can change like the weights. So right now they are just changing the weights, and it remains to be seen how can you change the activities of such neurons. So that's it from my end, and thanks for watching, and do like and subscribe if you like it. Okay, bye.